I start to record. Okay, starting. Okay, guys. In previous lectures, we introduced regular languages and finite automata to depict or represent a regular language. We discussed determinism and non-determinism, and we say that non-deterministic finite automata and a deterministic finite automata are equivalent in power. They are representing the same set of languages, right? So which means that there is no language which can be represented by a NFA but not with a DFA. No, there is no such a language. There is no such a regular language. Okay, guys. So, and this week we start context-free languages and context-free grammars. So I think you can just understand that these are more powerful. Context-free languages are more powerful than regular languages. And there are some languages that we can describe with context-free grammars, and we're going to see examples. Okay, guys. And I think today we just talk about these two, and next week we go talk about this green part. So let's start with what are the context-free grammars. Let me introduce them to you. Okay, guys. So the context-free grammars, guys, we have a collection of substitution rules like this. We are providing a set of substitution rules, a collection of substitution rules, and all they are also called productions. So this rule says that when you see a capital A, you can replace with a 0, capital A, and 1. Okay, guys. So these guys on the left-hand side are called variables, and they are represented with the uppercase letters mostly. So here, this A and B is also like a variable. And there are the terminals, 0, 1, and its pound key. And these are not produce any more strings, right? So A can produce 0, A1 or AB. But 0 cannot produce anything else. 0 is the last point. So guys, 0, 1, and this pound key, you can just think about them as like the alphabet letters. Right? These are our terminals, and these are our alphabet basically. And then the A and B, they're just variables. We use them to represent the context-free grammar. Okay, guys. So this A is also in the left top corner. This A is also called as a start variable. Okay, guys. And then what we do is we start with the A and replace this A with the rules, with any rule. Okay, guys. And now what we have it, there will be no variable left. All terminals, that we stop there because terminals cannot produce any more string. So it's going to be our string. So that you can just generate more and more strings by applying this rule. For example, we start with the A. We replace A with 0, A, 1. Okay, guys, by following the first rule. Second, we can also choose the first rule and generate 0, 0, A, 1, 1, right? So this A is here. I replace this A with 0, A1. So 0 is this 0, 1 is this, the last one, and these 3 are coming from this A. I replace it like this. And now what I want to say is that from this thing, from this string, I would like to produce the second. I want to follow the second rule, so that I have 0, 0, B, 1, 1. I follow the second rule, and then this is gonna be. I need to choose this one because there's only one rule for the B. 0, 0, pound key 1, 1. Okay, guys. So this is my string, and this is not the only string that I can produce, right? I can just say A is gonna be and B is gonna be terminal, so I can start with the pound key. Then I can just say A is gonna be the first one, A0B. I'm sorry, 0AB. Now I can choose B instead of A. Then I can choose pound key for the B, so that I can just say 0, pound key 1. Or I have 0, 0, pound key 1, 1. Or 0, 0, 0, pound key B1. So this is the set of strings that I can generate. I can produce with this grammar. So this gives me a language as well. Because what was the definition of the language? Is a set of strings. A language is a set of strings, so that by using this grammar, this context-free grammar, I can generate more and more strings. And all of them are give me a set. And by using this set, I can say that the language of this context-free grammar is this, right? Here's an example. So it's called derivation. Derivation in Turkish, türetmek. Okay, guys. So as you can see, we start with A, and A is our start symbol because it's on the left top corner. We cannot start with the B. That was a mistake. A becomes 0A1, 00A11, then 000A11, and then the final stuff is this thing. Final stuff is this string. And we cannot, so this is all terminals. All terminals. So you cannot say that, okay, this is my string. 000B111 is not your string. It contains this variable. But this is not your string. You have to have all terminals. And you have to use the substitution rules until you have all terminals. So that's also like you can just simulate it to a parse tree, right? So the first A becomes 0A1, right? The first A, we just have 0A1. Second A, you have 0A1. The third A, you have 0A1. Then for the last A, you just have B, and B, you have just the pound key. It's gonna be your string. The parse tree is important, just keep it in your mind. We're gonna define some terminology on this parse tree. So you can just represent it with a parse tree. It's the same stuff, right? Just visualize the stuff. So all strings generated in this way constitute the language of the grammar. And for this grammar, we have the language of the grammar. So what is the language of this grammar? It is basically 0n, pound key, 1n. Right? And n is bigger than or equal to 0, and n is, or you can do n is natural number. Okay, guys. 0n, pound key, 1n is the language of this grammar. L-B1. Like this. Okay, guys. So this is another way to represent languages. But we are showing that, I think you can see that already, right? We can show more language, we can show more languages with context-free grammars than we can show with the regular languages. Okay? This is a context-free language. And there's a rule, guys, like if you have, for example, for the A, you have two rules. A can be 0A1 or A can be B. Instead of writing the second line, you can just use the OR sign. This is a pipe, right? the pipe, or you can just use the or. You can use the or sign and just separate them like this for the shorthand. Or you can write it like that, but it's gonna be shorthand. Short way to write it. Okay, guys. So this is example, and this point like to describe a fragment of English language. So we just talk about the sentences right now, and it starts the sentence. And sentence comprise a noun phrase and verb phrase. A noun phrase can be a complex noun or a complex noun and a prephrase. Preposition, I think this prephrase. Yeah, preposition. And we have the verb phrase, and verb phrase can be the complex verb or complex verb with a prephrase. Each of them are just one. Using this thing, just one variable. Okay, guys, there is one variable. Prephrase can be prep or and complex noun. Complex noun can be article and noun, and complex verb or verb with a noun phrase. And these are the letters. These are the terminals that we have. Okay, guys. So by using this thing, we can generate many sentences. Like a boy sees. The boy sees a flower. A girl with a flower likes the boy. These are all coming from this context-free grammar. For example, with sentences, we follow noun phrase and verb phrase. And with the noun phrase, we just follow the complex noun. With the complex noun, we just follow article and noun. These are our rules, right? For noun phrase, we go complex noun. Noun phrase, we go complex noun. This one, we choose the first one. From the complex noun, we just have article and noun. And then verb phrase. For a verb phrase, we just choose a complex verb. For a noun, we just put a noun is a boy and verb is a sees. The boy sees. This is the way of generating this sentence. I think we can also say that by using these context-free grammars, we can actually represent the Java language, right? Or any kind of programming language that we have. And the answer is yes, we can do that. And actually, context-free languages are used in like the programming languages. When we use a parser, I think you heard the word, you know this what parser is, right? A parser follows this structure, follows the same idea. Of course, the grammar is for Java. It should be more complex, but the idea is the same. If you write something like that, like if A less than B, right? So your Java parser knows that if is a keyword and it must be followed by such a condition. And then it just try to find the condition. Parentheses, A and less than, B, the operands. Look for all of them. So it finds, it understands what you write, what you give as a source code to Java Virtual Machine. So parsers use the context-free grammars to understand what you give as a source code. Okay, guys. Let's look at the formal definition as we did for the finite automaton. Right? So finite automaton has a 5 tuple, but we have 4 tuple here. The tuple, which means is a sequence, so order matters. So we start with the V. V is a finite set called variables. Single set of a finite set disjoint from V. The disjoint, which means there cannot be overlapping. One symbol cannot be both variable and terminal. Okay, guys. So as a rule, like we just say uppercase letter for the variables, but lowercase letter for terminals, like here. As you can see, all of the variables have the uppercase letters, and all the terminals has lowercase letters. Okay, guys. So there cannot be any intersection between the V and the sigma. Okay, guys. Terminals must be disjoint from V, and they all must be finite set. There cannot be infinite. And then R is a finite set of rules. Each rule which will be a variable and a string of variables and terminals, and X is a start variable. So what you need to have is you need to have a set of variables, like in our example, these are A and B. Right? First we have V, a set of variables. Then we have sigma, a set of terminals. Then we have the R's, and R's are there. There are 3 R's, right? Set of R's. You can just see them here. And we have to start variable, which is A. These 4 gives you the formal definition of a context-free grammar. Okay, guys. In our example, this is what we have. This is what we have for our example. In this example. So here, let's say we have such a rule, okay, guys, and let's say we have, say, UAV. By using UAV, so we have this rule, we have the substitution rule. A can be replaced with a W, and let's say we have UAV, and U and V here are just strings, part of strings. And by using this string, we can produce or we can derive UWVY, right? By replacing A with a W, we can have this string. Here we say U terminal variable A, we yields UWV. Yields is the word, okay, guys? Say that. And if there's a sequence of substitution sequence starting from the U and ends with the UK, and there must be V as well. Okay. We say that this must be a V at the end. I forgot to add that. So we start from the U, and if there's some kind of substitution rules, sequence of substitution rules, and then finally we can just have V, we can say that U derives V. Okay, guys, if such a sequence exists. And we show that like this. U, let me make it here. U, arrow, we have the asterisk star, and then we have V. Okay, guys, U derives Z. So language of the grammar is this thing. So what does it mean? Which means that W's are element of your the set of terminals, right? With asterisks, so that you can just pick any of them. Also, the S, your starting variable, must derive this W. Right? There are W's, like all of them. Like if your sigma, what is this thing? Sigma star, sigma asterisk. If your sigma is 0 and 1, it takes all the zeros and 1, all the combinations that you can create with the 0 and 1. All the strings are there. It contains 0 and 1s. Because this is what does it mean, right? Sigma asterisk means that all the strings that you can generate 0 and 1 with the 0 and 1s, with zeros and 1s. What does it say? All the strings that you can generate with your input alphabet or with your terminals, but S derives them. S must derive those W's. This is your language. Okay, guys, this is the example. I think I can give the example previously. And this is the R. This is the R. Okay, guys, so let's see that. So this is the context-free grammar, as you can see. So it generates these. These are. Do I have an example? No. So let's do that. So can we just generate those or not? So we start with the S, right? I think first we have to follow the SS. I'm trying to just generate this AB, right? From the first S, I got the first rule. From the second S, I also generate the first rule. Okay, guys. Then from this S, I follow the last rule, epsilon, so it can be canceled out basically. And the second one, I also follow the same thing, so it's gonna be AB. So this is for the second, this is for the third, also this is for the third, and these are for, sorry, first one, right? These are first. This is first rule, this is first rule, and then these are the third rule, epsilon rule, so that I can just save the string. So what about the other one? All A's and B. Is that clear, guys? How can I generate AB? So to generate this thing, I think the second one, I just need to follow the second rule, I'm sorry, the first rule, and then first rule again, and then first rule again, and then the third rule, the last rule. So it's gonna be A, B, B, B. Is that clear, guys? What about this? A, B, B, B. Or A, B, B, B. Can you see how we can generate this? I see all that. So the first, any question, guys, about this? How we can generate this, the last one? Promise? You want to try it? This is weight of the neck, right? So AB is gonna be S, then epsilon. This AA and BB. S become SS. So this S becomes ASB, and this S becomes SS. Or the other way. Let me just do it. And then this S AASBB. No, I made a mistake here. It cannot be happen because there's a B. Then it should be SASB. No, I cannot do that, guys. Can you help me? How we can do it? Let me then do it like this. ASB and then another AS. What if this ASB? Then this is AASBB. Then this is I cannot generate one. For this S, I should say AASB. Then we have SB here, right? This must be go empty. This must be go what? Okay, I made it. Then we have to follow AA. This S goes empty. B, ASB, right? AB, BB, right? Yeah, then it's gonna be epsilon. Okay, I found it. Okay, guys. It's very hard. It's not easy to see sometimes. But we are not supposed to do that. We are not supposed to find a way to do that. So what is the rule for it? Can you say the rule for this thing? I think the rule says that there must be there must be same number of A and B, but number of B starting from left hand side cannot be exceeding number of A's. Like it's just a parenthesis. There should be a correct way to parenthesize them. Like if you think about the A is opening parenthesis and B is closing parenthesis, then it should be the way, which is how you can see it. Like this is A, this is B, A, B, or A, B, B, B. A, B, A, B, B. So there is no way to have something like that, like A, B, B. No. So this can be used for the parentheses to see that if the parentheses are correct or not. Okay, guys. Examples, guys, we have like expressions, term, factors. And these are for the multiplication and the summation. Okay, guys. You can just see more examples like this. And we have parentheses here as well as the input out in the terminals, and factors can be used with the parentheses. Okay, guys. So another example to generate these two strings. And you just any question, guys, before we start? Okay, so there's something called ambiguity, which basically some strings can be produced with different parse trees. Here you can see the example. Like by using the grammar that we just have previously, like this grammar, you can get A plus A times A with two different ways. Yes. So this is called ambiguity. And ambiguity is actually not useful, but we're going to talk about it later on. Okay, guys? Not that useful. But this is just showing a way to, there's no one way to generate one string. So if you cannot find a way, you can just try the other ways. Okay, guys? So after having all of these rules, like, okay, this can be the rules, and it's going to be hard to see that like this. To make things in an acceptable formal way, we have Chomsky normal form. So this is just a rule, okay, guys? It's just a form of rules where in a grammar, in a context-free grammar, all the rules must follow the same thing. A variable can be replaced with two variables or with a terminal. This is the rule. Additionally, we have a rule such like this. Starting state, starting variable can have the epsilon. Okay, guys. So why do we have this thing? Because we have to have somehow generalized way of showing the languages. Because like this is hard. Like having this different way, like this is having different way of showing it and seeing what's gonna be there is hard. like even if with a simple language. Instead, we should have a way of showing the grammars in which everybody can easily understand. To do that, we should have a form to follow. So that we have to convert, if you have such a grammar, you have to convert it to your Chomsky normal form so that people can understand it. People can see how it can be derived a strings. And then, like, there is a way of like this is the next couple of slides just explain how we can convert a context-free grammar into Chomsky normal form. Okay, guys. So let's say this is our example. If it is not a good, like it's not a very sophisticated stuff, you just need to like change or add some variables to make sure that it follows the Chomsky normal form. Okay, guys. For example, here, like if you have such a language and if you have such a grammar and you want to convert it to a Chomsky normal form, so these are just stuff. These are just steps that you need to follow. And then you start set, it says, like the change happen here in the bold, right? So just say S0 showing the S. It's going to be your start state. New start state. So new start variable. First one is first thing that you need to do is this. Second, you have to remove the epsilon rules. But by removing the epsilon rules, you have to add those rules to related space. For example, you would like to get rid of this rule, right? B can be epsilon, empty string. So that what you need to do is you have to replace all the B with epsilon as well, right? For example, S can be A and B, but if B is the epsilon, right, it can also be only A as well. And I add it here. A can be B, and B can be epsilon as well, so that B, I need to add epsilon here to show that A can be epsilon as well. Is that clear, guys? So, but then I can remove this rule. I can remove this rule. From now on, like this is going to be the same grammar, because if B can be epsilon, I just add a new rule for that to cover this rule. Okay, guys, and I have to remove this rule as well for the A. To do that for all the A's, I have to consider what if the A is epsilon or not. For this thing, what if the first A is epsilon? I just have SA. What if the second A is epsilon? I just have AS. What if both of them are epsilon? I just have S. Right? You have to consider all possibilities, all possible ways to get the A, and then you can remove this rule. Okay, guys. The third rule is remove unit rules, because these are violating the Chomsky normal form as well. For example, if I have S0 to S, unit rule means that there are two variables. So I have S to S here, I have S0 to S, and I have AB and I have AS. All of them must be removed. So first start with the S to S. I think I just deleted it because S to S meaningless, right? So I can just delete this thing directly. If I need to remove S0 to S, right, I have to put this rule here because these are the possibilities. S0 must be followed by S, and S must be followed by one of these. So if I need to remove the rule S0 to S, I need to copy everything here to S0 side. Then I can delete this thing. Okay, guys. So I do the same thing with the AB and AS because these are the same ones. So AB, instead of B, I can just write a lowercase b, right? I just delete the B and add lowercase b here. And here I need to remove A to S. If I remove the S, AS, I need to write this thing instead of S. But I have here. This is for the S, right? Coming from directly to the S. And then like you just need to add more variables and more rules to have two variables instead of just random number of variables. For example, instead of this ASA, what I need to do is, so I have this thing, right? A is ASA, right? So somehow I have to figure out how I can change it. If I just say something like that, A1 is equal to SA, which is in Chomsky normal form. Instead of this AASA, I can just type AA1, right? So that both of them are following Chomsky normal form. Okay, guys, this is of way of doing that. And if you need to write some kind of this context-free grammar and context-free grammar, then if you follow the rules, all of them, any kind of context-free grammar is convertible to Chomsky normal form. Okay, and the idea of the Chomsky normal form having a standard, having a form of describing a grammar so that people can understand what's going on there. Any question, guys? It's not that sophisticated stuff. We have to show it in the book. It shows. Okay, guys, push down automata. So, guys, push down automata is like, let's talk about non-deterministic finite automata. What do we have? We have states. We have non-determinism, so we can have epsilon rules, right? And we can read the input symbol, and we can check that whether we are on any kind of accept states, let's say, right? This is what non-deterministic finite automata can do. The pushdown automata has an extra component called stack. It has memory, which is not something obtained by non-deterministic finite automata. NFAs don't have memory, or they just have very limited memory to remember the input symbols, and that's it. Maybe the state that they are on, but nothing else. But stacks, with the push automata with the stack, we have infinite memory. Okay, guys, we have infinite memory by having the extra stack. So we can have the epsilon rules as well, and we can use stack as well. Okay, guys, so we have a non-deterministic finite automata with a memory. But stack has some kind of limitation, which is by nature of the stack, right? The access is limited. If you have such a stack, you can access only the top of the element, only top of the stack. You cannot read the bottom of it, or you cannot read the items below the top element. You have to pop it to see the next items. Right? Therefore, even though stack is, you can assume that stack is infinite, the access to stack is restricted by nature of the stack. Okay, guys. So pushdown automata can use the stack by writing symbols on them and then read them later. And writing a symbol push down all other symbols on the stack. So you can just push symbols to your stack, and then you can pop them. Okay, guys, I'm going to show you an example so that it's going to be clear for you. You basically read symbol by popping it and push symbol as well. Then you can just read them later. Let's talk about the language that we have. It's 0 to the n, 1 to the n. There are n amount of 0 followed by n amount of 1, the same amount of 1s. So this language is not regular. We show that with the pumping lemma. But can we show it with the pushdown automata? Let's see. Where is it? It's coming next slide, I think. The pushdown automata, guys, can be non-deterministic or deterministic, but we start with the non-deterministic one because deterministic one is harder to learn, let's say. And then, guys, pushdown automata is a formal definition of it. It's a 6-tuple. Okay, guys, I just want to show you an example here. Okay, this is a pushdown automata, a state diagram of it. Now I can go back and explain the formal definition. So guys, again, we have the states. State has the epsilon symbol as well. There is a non-determinism as well. But the difference is that we are not just reading one input form, right? We also manage the stack as well. So this means that, let me see. Okay, this means that first we read, I think, yeah, we read a input symbol, then we pop something, read, pop, and then we push something to stack. So for each input symbol you read, you can do two things, right? Pop or push. So you have to define that. By reading an input symbol, you can either pop something or push something, or you can pop push together. For example, what do you do is here, you read nothing from your input symbol, from your input string. You pop nothing from your input string, from your stack, sorry, right? Because your stack is empty. At the beginning, your stack is empty. Then you put a $sign here. So we put a $sign to mark the bottom of the stack, because there is no way for us to know if we reach the bottom of the stack or not. To see that, we push a $sign at the bottom of the stack so that we can understand by reading the $sign. We say, okay, this is bottom of the stack. Okay, guys, this bottom of the stack is infinite. We cannot follow it. Therefore, we push a $sign at the bottom of the stack. So first, let me repeat this again. We read nothing from the input string. We pop nothing from the stack, because there's nothing. And then we push $sign at the bottom of the stack. Next, if we read a 0, right? We read a 0 from input string. We pop nothing, but we push a 0. Let's say our input string is 0, 0, 1, and 1. So this is for the language 0 and 1 and, right? So let me keep it very basic. 0, 0, 1, 1. So I read nothing here yet, so I just jump to Q2 by pushing a $sign to the stack. Now I am reading the first 0. And it says that if you read a 0, pop nothing, but push a 0 here. And stay on the same state. Don't change your state. Is that clear, guys? Next, if you read a 0, I'm done with the first 0, right? If you read a 0, pop nothing, but push a 0 on your stack. And don't change your state. If you read a 1, right? If you read a 1, pop a 0. This is another, pop a 0, but push nothing. And go to Q3. If I read a 1, I pop a 0, but push nothing, and I change my state to Q3. If there is no 0 to be popped, then you just reject the string. Okay, guys, this is important. If you cannot manage, we cannot have correct stack state, which means that the string is violating your rule. Okay, guys. So after doing that thing, let me do with the wrong state, the string that is not acceptable, so that you can see what's going on there. If the string has a mistake or is violating the language. Okay, guys. I read the first one, pop first 0, and change my state. If I'm gonna read a 1, so this is like the non-determinism helps us here. If I read a 1, right, I read the one here, the second one, so I read both of them as well. Pop another 0, push nothing, stay on the Q3. And then you can read nothing, but pop $sign and go Q4, right? Pop $sign, push nothing, change your state to Q4. At the end, if your stack is empty, and then your input symbol is empty, input string is empty, you read all the strings, all the letters in your string, and you end up with the start accept state, then you say this string is accepted by the context-free language, context-free grammar. Okay, guys? Let me do another example with violating rules 0, 1, and 1. Let's say. So first, we push the $sign again at the bottom of the stack to mark it so that we know that where is the bottom of the stack. So that we stop it here, right? We can't read any kind of $1, so that we have to pop it, and okay, we know that the stack is empty. So we can go to Q4. 0. When we read a 0, we push nothing. I'm sorry, we pop nothing, but we push a 0. 0 is done. Then read a 1, pop a 0, push nothing. Yeah, I'm here. I'm reading a 1 here. Read a 1, pop a 0, but there's no 0 here. What I'm reading is $sign. At the top of the stack, there's $sign. So I cannot do that. It's violating. I cannot do that. I cannot run this thing on my stack because there is no 0, but it tells me that you have to pop a 0 here. Right? But I have a $sign at the top of my stack. I can say it's going to be violating the rule. Okay, guys? If we just say like 0, 1, 0, I think it's going to be the same stuff. Right? So 0, 1, I put a 0, 1, I put a 0, pop nothing, push a 0, I put it. I read a 1, I'm done with it. I read a 1, pop a 0, then push nothing. Then what about 0? I cannot read 0 here. You see, there is no rule for 0. I cannot read another 0 here. The rule is not defined, which means that I cannot do that, which means this is violation. Which means this string is not part of my language. Because my language is 0 and 1n. Right? The order is also matter, so this is not follow the order. So let's get the formal definition of the automaton, formal definition of the language. I'm sorry, formal definition for push the automaton. We have 6 tuple. The Q is a set of state as well, we know that. We have the sigma, the input alphabet, it's the same. We have stack alphabet as well, because we may push something different. Like $sign is, for example, is not part of the input alphabet, but part of the stack alphabet. Okay, guys. And this is transition function. It is very different format, as you can see. Not very different, but we also have a stack as an element. What do? We are on a state. We read the input symbol. It can be empty as well. And we are seeing the top of our stack, right? We are seeing top of our stack. Based on that, what we do, we change the state, and we can just change the stack symbol, right? Can be changed. Of course, we can just pop, or we can just put something. And then we have Q0 and F. Q0 starts it, and F is accept states. Instead of accept states. Okay, guys. Is that clear? The only difference between the push automaton and like non-deterministic one, non-deterministic finite automaton is that the stack. Since we have a stack, we have to change transition function accordingly, and everything is the same. Else is the same. So this is like computation, and like only let's stay the same thing. Like this is what we said previously, but in a mathematical way. It basically says that you have a bunch of strings m except w's if w consists of some w's, w1, w2, wm, and each of them are part of your input alphabet. Each of them just one letter. You have a bunch of states r0 to rm. They must be part of the queue, so that there must be some strings, right? S0 to sm, element of your stack alphabet. They must be so. These w's, these r, these s must exist, where r0 equal to q0, s0 must be empty. Right? Your start state must be empty. And then for all of the rules that you can have, like for all of the changes, you have to have a rule for them. This is what it says basically. So as you can see, this is like the R. For example, guys, let me do an example. Let me show you one example. Okay. So we have this thing, right? I'm gonna explain what does it mean. So we have this Q1, then we go to Q2. We have epsilon, epsilon, and dollars. Push. Yeah, dollar sign. Okay, guys. So here, our R0 is, right? R0 is Q1. So we are on Q1. We are reading epsilon. On top of stack, we have epsilon. Right, this is it. This is what it says. Okay, guys. And then what we do is there must be a rule. There must be like a transition that take us to Q2, right? Q2 with a B. And our B is what? Dollar sign. Is that clear, guys? Like, if the rules, such a rules are existing, if such a rules exists, and all of them are 0, 0, S0 are the part of the R0 part of the Q, S0 part of the dollar sign, the stack alphabet. Then what you say is that if this thing is like, if you can just have such a rules like this, bunch of rules, then you just say it's gonna be accepting. Okay, guys. So for example, for the second 0, our Q3 doesn't have such a rule, right? So our Q3 with a 0, with a, what does it have? Actually, this doesn't say anything here. But let's say epsilon, it doesn't matter. This is not defined here. When you're on Q3, you cannot read a 0. This is not violating. That's why this string is violating the language. That's why it's not part of the language, we can say that. This is just a mathematical representation of what's going to be inside of the language. Okay, guys. So this is the like input and stack, as you can see. So input, if your input is 0, right? It says when you're on Q2, oh, it says that if your input is 0 and you are on Q1, it's not defined. If your input is 1, you are in Q1, it's not defined. If you're on Q1 here, right? If you're on Q1, if your input is epsilon, then this is what you need to do. Go to Q2 and push dollar sign. This is the transition function, guys. If you are on Q2 and at the top of the stack, you push nothing, right? But you pop nothing, but you push a 0. So this is the rule for the Q2. Or if you see a 1, right? You push nothing, right? And change the code to Q3. Is it clear, guys? So this is the way of like how you can just read stack, or how you can just define the transition function. But it's basically like this. This is read, this is pop, this is push. This is all just mathematical representation. You don't need to Like you can understand easily. You just need to read them thoroughly. With a little bit carefully reading, you can see that. Okay, guys. So I'm aware the time is up, but just I think we just have 10 minutes left. After 10 minutes, we can just stop it here. Okay, guys. So this is just transition function. The important part is that you need to know that this is the first one is for reading, second one is popping, and the last one is for pushing. It is the same with the everything else is the same with the Planet Automata. Transition, the rules, everything is the same. But also you have the stack that you need to look at it. Okay, guys. Here's example, the same example. It says that $sign symbol is used to mark at the end of the stack because we don't have any mechanism to check at the end of the string. Okay, we can't check that. It's the stack is ending or not. And we have to this rule, we have to this transition to make sure that before going accept state, we pop the $sign. So this rule, we make sure that before reading any input symbol, we push the $sign to mark at the end of the stack. And then we use this transition Q3 Q4 to make sure that $sign is popped before we accept the input string. Okay, there are other examples that are somehow complex here than the other, more complex than the other. So this is the rule. We have three input string, A, B, three input letters, A, B, and C. And the rule says that either I must be equal to J or I must be equal to K. A to the I, B to the J, C to the K. Okay, guys. So we use non-determinism here. It was the same with this one. It was the same with the idea is the same, but we use non-determinism. So this part is for like the same thing, push $sign. And we just need to count how many A's that we need, because like at then we need to see if either J's or K's are going to be equal with the I, right? So here by reading A's, when I'm reading an A, I push A here, right? So I push as many, how many, the number of A's I push is the same with the number of A's that I have as the input symbol, right? If I have A, I am one of them. After I'm reading all of the A's, my stack has the $sign at the bottom and A's on top of it, and there are 5 of them. Okay, guys. A's are there. Then I'm use non-determinism because it says all right. Either B number of B's or either number of C's is going to be equal with the number of A's. And therefore, I just use non-determinism. So this one is for this one is for J is equal to I, right? So that after I go here, let's say if I'm going to match I and J's, right? Reading each B, with reading each B, I just pop an A. I read the B, pop A's. Read B, pop A's, and push nothing. I'm just popping A's. If they're the same number, right? I should be able to pop $sign as well. And then number of C's doesn't matter. I can have as many C's as I want. When I read a C, I do nothing on my stack. Because if I have A's and then followed by same number of B's, right? I, let's say, it doesn't matter how many C I have here, because K can be bigger than, equal than, bigger than 0. It doesn't matter how many of them I have here, right? Doesn't matter for me. That's why I just don't care about the C. If I go to bottom side, bottom part, or the right path, in which I try to match I's with the K's. Okay, guys. Reading B's, nothing happens because I try to match K. These don't affect me. I can have I amount of A's, then no B's, then I amount of C's. For the second part, for the bottom part, bottom half of the diagram. This is just consuming B's. I don't care about them. But this part, with this, what do I do is, by reading C's, I am popping A's again. When all the A's are popped and there's nothing else, by reading nothing, I can just pop to the other side and go to the except state. Right? So this is the way of doing that. We use non-determinism to choose path because it says or. This way or this way. Okay, guys. Another example. R means written backwards. Okay, so it should be something like that. If I have 0, 1, 1, must be 1, 1, 0. Right? This is what it says. So I need to create a palindrome here. Let's look at this one. We have again, we push the other side to the bottom of our stack at the beginning. So it says if we read a 0, we need to push a 0. If we read a 1, we have to push 1. Basically, you write what you have here, right? By using non-determinism, you don't know where is the middle point, but by using non-determinism, you can just jump this stage, right? Because if you remember, non-determinism lets you run all possibilities in parallel programming, right? Simultaneously. In our example, 0, 1, 1, right? Then 1, 1, 0. If I read a 0, I push 0. If I read a 1, I push 1. If I read a 1, I push 1. I'm going to read a 1 here. So that I need to just, well, how do I know that I need to jump on the Q3? Thanks to non-determinism. Only one path should be working. And like right now, we know where's the middle point so that we can just cut it from there. So we can jump here. If you read the 1, you pop a 1 and push nothing. I read this thing. If you read the 1, pop 1 and push nothing. If you read the 0, pop 0, push nothing, and everything is done. Read nothing, push $sign, and end it here. Okay, guys. So these are the languages that we cannot define with a regular languages. These are not regular languages. These are context-free languages. And they need to, so we have to remember how many zeros or how many ones we read before we jump to the second line, right? So we have to remember, if you need a memory, that's not a regular language. So that's why 0 and 1n is not a regular language. So you have to remember how many zeros you read before you start reading ones. Okay, guys. So this is the same thing. Context-free grammars and push-to automatas are equivalent in power, which means that they are going to be they are going to be capable of describing the context-free languages. They are going to be equivalent. But then we have to say that if a language is context-free, if and only if some push automata recognizes it, right? So that we have to show a way, an algorithm, to convert a context-free grammar into PDA and vice versa. Okay, guys. And these are the next big topic. Any question? So I think we are done with the first part. Non-context-free grammar and then context-free languages. So I'll see if I need to show them. Maybe we can just jump to non-context-free language and context-free languages next week. I have to see the syllabus if I'm gonna tell them or not. This might be a little bit advanced, that's why I'm saying that. Any question? Okay, guys, then see you next week.